even though my technology was being, I kind of am very appreciative of that fact because I feel like the conversation that you just had was pretty awesome. I think it was pretty awesome. Huh. All right, so talk to me about what you figured out. Should we bring, oh yeah. Bo is advocating for C and saying that C is the only one that works. Do you want to tell us why you think that? So the change in angle, right? And you are saying that, I'm just trying to like put it in the right form, right? Is saying final minus initial. Whoa, hello. That's supposed to be a theta. Is 4 rate. Whoa, for real? I love technology. Okay, it's 4 radians. Okay. So, and where'd you get the pi from? So 180 degrees is equal to pi radians. I don't know what is going on, and this is really ridiculous. It's like, yeah. Okay, so you got pi radians, which is 180 degrees. I'll get my other good one to see if it works. I don't know if that's the problem or if it's the OneNote thing. We'll find out. All right. Is that making sense? Yeah. So 4 is the only bigger difference than 3.14, which is what you have to have pi, right? Because you got a difference of 3 here and you got a difference of 2 here, right? So those are both too small. Yeah. Yeah. Good show. A couple of quick things here, just because we're gonna see them later, and we want to make sure we know what they are. There's this phrase called rigid body. What? That's a weird thing to say, right? So we haven't really talked about what a rigid. But you know what the word rigid means? Stiff. Yes. So it's a stiff object. It's an object that has a shape, and that shape is not going to change. Okay. If you take some object, like a water balloon, let's say, okay, and you start to spin that water balloon, is it going to stay a nice, happy little round balloon? Do you guys think? What's going to happen to it? Do you know? Right? Would you describe that as rigid? I would not. No, that would be a non-rigid body. Can we study those? Yes. Are we going to in this course? No. Rigid just means that it is solid and it's not going to change shape. Body just means object, right? It can be one thing or it can be a set of things. So this is a rigid object, a not changing shape of object that's turning about a fixed axis. That's all it is. Were there any other weird words in this question that you wanted to ask about before we move on to part B? Okay, let me give you part B of the question. Here it comes. Suppose that the change in angular position, you can't really see that. Let me add some more space here so you can see it a little bit better. Insert some space. Oops, come on. Insert some space below. There we go. Suppose that the change in angular position for each of the pairs occurs in 1 second. Which one, A, B, or C, represents the lowest average angular speed? Okay, I'll give you just a minute to take a look at that. Lowest average angular speed. All right, let's do it. So what did you say? Suppose that the change in angular position occurs in 1 second. Which one represents the lowest average angular speed? B? Yeah? Why are we saying B? Shortest distance, shortest delta theta over time. I'm frozen. It didn't even make those crazy things. Is equal to omega. Omega is angular speed. Yeah? Smallest angle, same time, smallest omega. All right, last one. I'm going to make it a little bit smaller just so you can see the numbers one more time, maybe. Can I do it? Come on, silly thing. Nope, maybe not. I'll just make it a little smaller. There we go. It asks you to consider again the pair of angular positions above. If the object starts from rest, okay, at an initial angular position, and moves counterclockwise with a constant angular acceleration and arrives at the final angular position with the same speed in all three cases. For which choice is the angular acceleration the highest? I'll give you a minute to chew on that one. I like this one. It's a thinker. All right, my friends, let's discuss. Where did you come out? Or where are you at in your conversation? A, B, C, all the same? All zero? Probably not all zero. You were having great conversation. Can you tell me what it was about? Or maybe don't tell me the answer, but tell me where you started. Josh, where did your conversation start? It was just you. Well, a conversation in your head. Okay. Say that again. I think what you're saying makes sense, but I'm not positive if I understand what you're saying. Drew's got his hand up, but I want to come back. Is that okay? Go, Drew. Does that make sense? So I want to make sure I'm understanding what you're saying. So in case B, delta theta is the smallest, right? That's what you're saying? And then keep telling me more things to write down. Okay. Okay, so V or omega final is the same for all. Okay. So if omega is the same for all and it doesn't have very far to go, then that means that the time is going to be shorter as well. Is that kind of what you mean? Or the distance that you're traveling? I'm just trying to like put it into some physics reasoning. Like I feel like I understand where you're at kind of, but I'm not quite. I don't have physics to ground it. Can you help me ground it in some physics? There is physics to ground it in. Like I feel like your gut is telling you exactly what is right. Chris, you were reacting to something. Right, and that is a key here. And I heard some people asking. That's what I thought I heard you ask. The time is not necessarily the same for all of them. Yeah, the time is not necessarily the same for all of them. We know that the initial velocity is the same, and we know that the final velocity is the same. We know that the distances are different. The times may or may not be. Do you want to say something, Lucy? No. Just thinking with your hand in there? Okay. Okay. I'm going to hold on to this. Go ahead. It's just that we're just not saying, all we're saying is that the time for this one to speed up to a final velocity is not necessarily the same as the time for this one. As it needs, yeah. This is what I'm going to suggest. We do this sometimes. We're going to come back to this question in just a minute after we've gotten a little bit more physics under our belt. Because I want to support that gut feeling that some of you are having with good solid physics that we know. Is that fair? I guess, she says. Like, do I have a choice, Ms. Carveling? No, you don't. So here we go. All right. I'm going to go back to the front of your sheet here. We're going to write down a couple of things. There's some space at the bottom of your page that you can write this on, or you can write it on the back. I'm going to write it over here just so that I can kind of reference some things here. Because I promised you yesterday that we would talk a little bit about radians and about angular frequency. And I want to do that. I didn't want to, not be truthful. I know that some of you have a loving relationship with the measure of radians. Some of you do not. And I want to make sure that we all feel good about them. So I'm going to tell you a little story, okay? It's a little story about when I used to teach math way back in Des Moines, way back, right? And I used to teach about radians to my eighth graders that were taking geometry. And the best way to get eighth graders to engage with mathematics, I found, is to engage them with candy. Okay, and so what I would do is I brought Smarties. Do you guys remember what Smarties are? Those little circular candies. Sometimes we did Smarties. Sometimes we did M&Ms. And I would give them a piece of paper, a piece of graph paper like this that had a bunch of circles on it. Okay, and then we would do this little game. And did you guys? I don't know if you guys did this game when you were in math when you were learning about this, but now you can shake your fist at those math teachers that didn't do it. Here we go. So I'm gonna line up little Smarties along the x-axis, a radius of 3 out, and then I'm going to follow that circle up, and we actually went all the way around the circle, but I don't want to waste time doing that. And then I would go out a couple more, and then I would go up like this, and we would line up our little M&Ms like this, or our Smarties or whatever, and then we go out a couple more, and then we do the same thing, and we'd count them up. And the really interesting thing that they discovered from this, and that you probably at some point in some mathematics class discovered as well, is that the game, the reason that we love radians is that it's just a ratio. That is all that it is. The ratio of the radius, or the arc length to the radius, arc length to the radius, arc length to the radius is always the same. That's all it is. And if you do the ratio of the arc length to the radius going all the way over here, do you know what that ratio gives you? Just a little over 3. And if you do the arc length to the radius all the way around the circle, do you know how it gives you? A little bit over 6. Yeah. And if you get a ratio of 1 to 1, you get an angle that goes up like this. Anybody want to guess how many radians that is? 1. When the ratio is 1 to 1, then you get that same angle all the way through. Okay. A radian, 1, 2, 3, 1, 2, 3, goes like this. Whoop, and this is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7, if I draw it right. All that it is, a radian, is just the ratio of arc length, or part of a circumference, divided by the radius. Okay? That's all it is. There is nothing to be scared about. Somebody in 7th hour yesterday was asking, what's the unit for radians? And there really isn't one, because it's like meters over meters or centimeters over centimeters. It doesn't matter. It's just a placeholder, because it's just a ratio. That's all it is. Okay? When you go all the way around what we would consider 180 degrees, so halfway around the circle, the ratio of arc length to radius is 3.14. And if you go all the way around, it's twice that. That's what we're talking about. Okay, so I just want to let you know that it's really not scary. Okay, because I know that for some people, it's just like there's a lot of anxiety that comes with radians. And when we do rotational motion, we deal with radians. And I don't want you to get like so anxious about it that you just like shut down and don't want to play with it anymore. Because I know that that happens. I totally get it. Does that make sense? Is that okay? It's a beautiful thing. Radians are really pretty awesome. Okay. You can also remember here, if you're trying to keep track, that 360 is equal to 2 pi radians. And we're going to use that knowledge in just a second as well for some other things. We need to know how to do those conversions now and then. The other thing that I wanted to share with you, that you might want to throw in some notes here, is about omega. We said omega yesterday was angular velocity. I also mentioned that it was angular frequency. And this, you guys, we talked about this about 2 months ago. We talked about omega when we were talking about the simple harmonic motion, bouncy, bouncy, bouncy stuff. And I introduced you to omega, and I said, just wait, we'll get there. And now we're there today. Okay? Omega is change in position divided by time. If we go all the way around a circle, how many radians is that? 2 pi of them, right? 2 pi radians. And it takes how long to do that? It takes a period. Does that make sense? A period is the time for one full revolution. So we can also write omega as 2 pi over t. Okay? Or we can write omega as 2 pi times frequency, f. And that's why we often will call it angular frequency. Because it's literally how often does it go around the whole circle? That's all it is, right? It's radians per second or a full cycle in a period. That's all it is. So the units generally when we're talking about these things are in radians per second, but sometimes we will refer to them in hertz, just because radians doesn't mean anything because it's a ratio, and then per second is just in hertz. How are we doing? So far, so good? Sweet. All right. I got one more thing here, I think, that I wanted to tell you. Is that right? Nope, we're going to do one more thing. The other thing and I'm actually going to write this one down on the bottom because I am going to insist that if you haven't written it down here, you do now, and that is converting from translational to rotational and back. Okay. We know translational stuff really well. You know it, you understand it. It's deep inside your core. Rotational is a little bit newer. We don't spend our lives, I mean, it's kind of ironic. As physics teachers, when we sit down and talk about why rotational motion stuff is so hard, we talk about it because, you know, everything that we see goes in a straight line. I was just about to say, we don't spend our life doing things in circles. Let's be honest, we're on the earth, right? The earth is doing circles all the freaking time. And the earth is going around this, like, we live in this rotational world. We just don't recognize it in that way, okay? But we can convert really easily between them, and that's really nice. So I'm going to jump back here to our definition of what an angle is. We said an angle is the arc length divided by the radius. The arc length is really just a distance. So this is really just a distance divided by the radius on the circle. So that's the part of the circumference you traveled divided by the radius. And so then we can solve that for x. And we can say that the translational position or displacement, I guess I should probably write these as deltas just to be a really good kid, okay, is equal to delta theta times r. We know, that delta x over t is equal to v. Yeah, we've known that for a while. And so instead of writing v, we can write this as, oh, hold on, just make sure I'm doing this right. What did I just do? Oh, we can write that, yeah, as, sorry, I just lost my train of thought. Delta theta times r over t. Hey, what's delta theta over t? Omega. So we can also say that v is equal to omega times r. Okay. We can take it one step further. We can say that delta v over t is equal to a, which really just happens to be omega times r over t, and omega over t, or change in omega over t. Angular acceleration, what letter is that? What do we call it? That's a really good question. Alpha is what we call it, absolutely. So we can say that a is, oops, not proportional to, is equal to alpha times r. So if you're going to circle something, remember something, this is the thing to remember. Woo! Right there. Okay. These are the nice conversions between the translational stuff that we know and love and understand really well, and the angular stuff that we're now just getting our hands dirty. Okay. Just a nice little reference. We're going to try a couple problems to get our heads around this. I'm going to go right over here. I've got a little ranking task for you to look at. Here it comes. Whoa, it's really big. Let's make it smaller. There it is. I've got some, they look kind of like bowling balls to me, but I think they just are spheres, hollow spheres, not drawn to scale. rolling at a constant rate without slipping. So they're not drawn to scale. In fact, we're going to figure out the radius of them, so they just didn't want to give it away. Which picture is bigger? Like that would be a lot easier to do than actually doing the physics, right? Okay. All of the spheres have the same mass, but their radii is where they're, as well as their linear and angular speeds vary. The task asks you to rank the radius of the spheres. Give you just a moment to do that, okay? Have a little conversation. Once you have come up with an answer at your table or at your pair, go ahead and get a whiteboard, because we're gonna do a couple things that whiteboards would be helpful for. So once you're ready to, go ahead and grab a whiteboard, and then we'll continue in just a sec. Take a look at the other people's. Did you agree? Do you all agree? B, C, D, F, A, E? Yeah? Do we have all of our tables in agreement? B, I hope it's right. I know, but I want to write it down first. What is it, C? What'd you have? D, F? So you all have the same thing, which usually is a good omen, but you never know. So talk me through what you did so I can verify that I agree. How'd you figure it out? Elena, do you know what you did? What'd you guys do? Yep. Yeah, you just did it, right? That's awesome. So you do like V divided by omega gives you R in each of those cases? Yeah. Nice. High five to you guys. Nice work. All right, ready for more? Yes, please. All right, here comes another one. This one is not a ranking task. It comes from the same people, though, but it's a little different. Here it is. Whoa, it's graphing. Welcome back to graphing. I know you missed it. It's back. So, friendly reminder that everything you know from translational motion translates over. Yes, I did that. Translates over to rotational motion. It's the same game. So here we've got a situation. It says sketch the angular acceleration versus time graph, given the angular velocity versus time graph shown for the same interval. If this was a V and this was an A, you would have done this in October with a smile on your face. I'm confident. I want you to take this. I want you to make an omega versus time graph and make it into an alpha versus time graph. Have a conversation. Write one on your whiteboard. Let's do it. You got this, guys. Hey, what? I have an answer. All right. I want to see some graphs. They don't have to be perfect. We're just getting the idea. You see, I can't see your pretty graph. Oh, you're going to show everybody else. I love it. That's okay. No, it's all good. So I see a lot of this. I just want to make sure you guys are all with me here. So you were up here until 2. Oh, it's indeed frozen. I appreciate it so much. Thank you. And now it goes down. And it went to 0 for a second or a minute or a unit of time, whatever that was. And then down. Yeah? How did you know? Because you just know. Is that going to be a sufficient answer on an AP exam? How do you get from here to here, guys? What did you do? And why is this one bigger than this one is little or smaller? Yes. Yeah. How are we doing? We okay? Good for you guys. Yay. So the nice thing about this, and friends, the reason that I do this now is because it's been a while since we've done this, right? With your regular translational stuff. It's a great review. It's a great review for the stuff that's coming in May, right? So it's good for us. Speaking of good review, here's another one for you. I'm just going to leave this here and let you read it, because I feel like if I read it to you, it's going to get more confusing. I'll give you a couple minutes. You get to draw 2 graphs this time. You're welcome. Have fun. Don't whine, just do it. You got this. All right, we're going to start a conversation, but I don't want to see your boards yet. What? That seems mean. I'm sorry. Before I want to see your boards, you don't have to flip it over. It's okay. You don't need to fight about things. Before we do that, I want to know what's going to happen to this pulley. So first of all, are you guys understanding what's going on? So you know what a pulley is, right? It's like a little wheel on an axle that can spin. So you've got a weight here, and if I just put this weight on the pulley and I let it go, where's it going to go? It's going to go down. You with me there? But is that what's happening to this little mass that's over here? No, it's going up, right? Up it goes. So that's what's happening. It's rotating counterclockwise and the mass is going up. Is it going to keep going up forever? Morgan says, no. What's it going to do eventually? It's going to go back down. So that weight, if we just looked at the weight itself, it's going to go up and then it's going to stop at some point probably, and it's going to go back down. But if we're talking about the angular velocity of the pulley itself, so it's got this positive angular velocity, and then it's going to stop at some point, and then it's going to go which way? The other way? Is that what's on your picture? Check your graph. Is that what you have? Yeah? And then once you do that, then the acceleration graph should be pretty easy to draw, right? Because you're just looking at the slope. So in this case, the angular velocity starts positive, negative, or zero? Starts positive, and eventually it's going to go negative. At some point it's got to go through zero. Is it going to be a curve? Is it going to be a straight line? Is it going to be loopy? What's going to happen? Straight line with a slope positive, negative, negative. Something like that. It's supposed to be a straight line, but my stylus is not allowing me a straight line today. You get the idea. And if I do that, then what is the angular acceleration graph going to look like, friends? Straight line, negative, negative what? Value, negative slope, negative what? Slope of zero? Something like this. Yeah. How are we doing? We okay? We still have time, right? We got four more. Only 2 minutes. Okay, we got to do 2 minutes worth of stuff. Here it comes. You need that gold sheet out. I know, it's mean, right? We got 2 more boxes to fill in. What? Nope, it's going to be great. Here we go. It's totally great. Stop whining. The more you whine, the less we do. VF is equal to VI plus AT. Do you agree? Can you translate that into the rotational business? Instead of V, you're going to write omega. Instead of A, you're going to write alpha. And time is time. Let's do another one. My favorite one. Delta X is equal to VIT plus 1/2 AT squared. It's been a while since you played with these. They're back. Oh, yeah. Delta theta is equal to omega initial times time plus 1/2 alpha times squared. Friends, now that you know all of the kinematic stuff, this is easy peasy. You got this. Okay? When you do these problems, givens, unknown, equation, substitute, solve. You got it. One more. Here it comes. VF squared equals VI squared plus 2A delta X. You translate that one. You can do it. Use the rotational variable. It's the same darn thing. What's it going to start with? It's like you could have written this down or something, Eden. What? Omega final squared is equal, what's going to be the next thing? Omega initial, right? Squared plus what? Okay, then what? Oh my gosh, and then what? Oh my gosh! Whoa, it's amazing. The homework that you have for tomorrow is over this step. You got to use these equations. Use the guess method and you'll be set. Bye!